Okay. I hope I'm audible. You can hear me properly, and my slides will be visible just in a moment. So let's continue with yesterday's discussion. And we have been talking about coal bed methane, and we were talking about its permeability, and we said that the permeability of coal bed is primarily dependent on its fracture system, and the inherent fractures uh, of coal are called clits. There are two types of clits that are present: face clit and butt clits. Face clits are the primary clits. They are the more continuous ones, which forms parallel to the direction of maximum horizontal stress. We said why in the last class. And then there are secondary clits, which are smaller clits that essentially connects face clits and forms the whole fracture network. We also said that clits do generally form in the bright bands. Okay, in the bright bands. So bright bands are the bands which are vitrinite rich bands, which are formed by the woody material. Okay. And the origin is linked to the dehydration devolatilization process during qualification. And we talked that if in an area, if there are more number of open clits, we will get higher permeability. Uh, and of course, we also said that the clits could be kind of clogged by mineral precipitation, be it calcite or quartz. This is where we ended yesterday. And this is how the analogy of facet and bucklets goes. If you think about, you know, um, that there are only face clits present in a particular coal system. What I observed that there is only one way traffic. You know, the cars. You can put an analogy with a busy traffic system. Yeah, maybe this one is taken somewhere in China, where you can see there are dividers between roads. Okay, and the cars can actually pass through these only through the lanes, right? So there is no mixing of the car. Okay. So that the cars will flow smoothly, but there will be no mixing of the car. And this is the situation if we would have had only face plates. But then, of course, the situation for coal is more like India, which is a picture taken in India where, the roads do meet. This is one road and there is another road which actually meet. And there is a little bit of chaos, but then still there is a good amount of mixing between the cars and between different types of vehicles. And that's what happens in a coal bed. The longer pathways which are formed by the face clits are often intercepted by the butt clits, which are the smaller ones, and they essentially form a pretty robust network. Now, one thing that we wanted to talk about how coal permeability varies with depth, and this is a good representation of such data. What you can see here in the x-axis, depth is increasing, and in the y-axis, permeability towards down, it's decreasing this way and increasing this way, and this is how relationship goes. It's quite asymptotic. And then you can see that with depth permeability decreases, right? Although there is a large scatter in the data. So it's not only the depth which controls permeability, but depth is a major function that controls permeability. Okay. So permeability decreases with depth. There is a huge variability and hence uncertainty. There is no as such defined definite trend, but this is also subject to interpretation. But one thing for sure, with depth, permeability actually decreases. So what essentially happens that suppose if I draw a clit, suppose this this part is my clit's aperture, the open space of the clay. Okay. So with depth, what would happen? My effective stresses will increase, and hence, the space between these walls, okay, these walls, the space this between these walls will tend to decrease, okay, and I will get less and less aperture as we move uh, with depth. Okay, as we move with depth, we will find less and less aperture, and hence I will see there is a decrease in permeability. Okay, now there is another interesting thing about the permeability of coal. That is, for example, if I think about the permeability of a sandstone reservoir, permeability of a sandstone reservoir, okay, and say, for example, this is a reservoir from where it has started producing hydrocarbon, okay, and then what I am saying, I am plotting permeability against time of production, okay. I mean, this is, say, for example, at January 2021, one particular field starts producing, and then I am plotting the permeability value for next 30 years or so. I will see more or less the permeability stays constant with time. Okay, so there is no significant change in the reservoir permeability, but the permeability stays more or less uh, constant with time for sandstone reservoirs. Okay, for conventional reservoirs, but in case of unconventional reservoir like coal bed methane, the permeability is little bit difficult to understand, and this is what I'm going to demonstrate now for you. So what happens here is if I now plot permeability, okay, with time for a coal bed methane field, for a CBM field, but I will observe that the permeability initially decreases and then the permeability increases. So there is an initial decrease, is characterized by initial decrease and then subsequent increase. Okay. And why does this happen? This happens because of two phenomena. You understood, right? So with time of production, right? So initially you produce a lot of water and then you start producing gas. So this is more or less the time of dewatering. Okay, this is more or less the time when you dewater your coal seam gas, and then this is the phase more or less your gas production. Okay. So what happens while you dewater? I'll try to explain why this one happened with a simple sketch. Moral of the story: the permeability decreases with the permeability changes with time, production time. In the initial period, the permeability decreases, and with time, the permeability increases again. So, what happens in this case physically, if I want to understand, I have to coin two terms here. One we call as matrix shrinkage, and the other one is called um, matrix swelling. Okay. So we will explain these two phenomena for you. So let us see what matrix shrinkage is. So for example, okay, let's just say first matrix swelling, and then we talk about matrix shrinkage. Okay, matrix swelling. So what happens at the initial stage of production? Suppose these are my coal matrix, these blocks, and the space in between is my coal permeability. Okay. So coal permeability means that portion will be completely filled with water, right? This is completely filled with water before production in that cleat space. Now, by dewatering, what I'm trying to do, I'm taking the H2 out. So now if I take the H2O out, what would happen? The in the next phase, if I take some significant H2 out from it, so I have started taking H2 out. So what would happen? This matrix will start to swell. Okay, because of the pressure release, the matrix will start to swell. So if the matrix starts to swell, what would happen? The space which was actually left by water, the cleat space will virtually decrease because the matrix has swelled. Okay, so the permeability will tend to decrease as well if the H2O is out from the system because of the matrix swelling. Now, after a while, there will be gases being diffused from the matrix. That is what we talked about, right? And then there will be a point when gas will start to diffuse out from the matrix to the clit system. Now, while this diffusion process takes place, when the these molecules actually comes out, the gas molecules um, comes out to the clit, there is another phenomena starts to happen, that is what we call as matrix shrinkage. So what happens in matrix shrinkage? The swelled permeability, the swelled clit boundaries will again go back. Okay. So in the next phase, what I will observe that my boundaries are again going back. Okay. Matrix again shrinks. So if the matrix again shrinks, I will create more space in the clit, and my permeability will again be enhanced. So hence I will observe a pattern of permeability like this, where it initially decreases and then it increases. So this decrease in permeability is to do with the dewatering, and while dewatering, what happens? The coal matrix essentially swells. As a result of that swelling, the space which is made by the cleats, the open space which is responsible for the permeability, actually decreases, and hence the permeability decreases as well. But at the later phase of the later lifetime of the CO2 of the carbon dioxide project, sorry, TBM project, what I observed that while the gas starts to produce, the matrix again shrinks, and because of the matrix shrinkage, the effective aperture of the clit system increases, and hence we find the permeability to increase as well. Okay, is there any question at this point? Let me see. If you have any question, have you understood matrix shrinkage and um, matrix swelling? Pratichi, can you tell me if you have understood?
Yes, sir.
Is it clear for you? Matrix
Yes,
shrinkage, matrix swelling. Okay, and that
yes.
would essentially lead to permeability change. Okay, initially permeability will decrease and then permeability will increase. And that's outstanding phenomena for coal bed, which doesn't happen in any other reservoir. For any other reservoir, the permeability stays constant for the rest of its life. Okay, let's continue then. Okay. So you can see here the basic matrix porosity and fracture porosity, and matrix permeability and fracture permeability is denoted. Okay. So you can see here. Okay, so this is the microporosity present in coal seam. So very microporosity present in coal seam. Okay, which actually emits gas by disruption, and then mesoporosity, which is little bit better. which emits gas by diffusion, and then natural fracture, where the gas flows following Darcy's law, okay, laminar laminar flow, okay, Darcy's law, and then of course, so from microporosity it comes to mesoporosity, from mesoporosity, so from microporosity to mesoporosity it comes to disruption, from mesoporosity to the natural fractures it goes through diffusion, and within the natural fracture and in the induced fracture, the fracture which are called the flax, the hydroflax essentially which we create in the well, that is where the hydrocarbon actually moves following Darcy's law, okay? And then it eventually comes out through the well. So if you look very closely, what I will find that there could be very, very small scale cleats, which we called as microcleats. There could be slightly larger cleats, which we call, mesocleats, of course. And then these micro pore spaces. Okay. So as we talked about that in the microporosity, it is generally dominated by adsorption process. The transfer is dominated by diffusion process in case of mesoporosity, and then of course in the natural fractures, it follows Darcy's law. Okay, so you can see here that. These A and B, these particles of gas that actually comes out through the process of disruption from the microporosity, and then it diffuses to the clit system, okay? And then here this flows following Darcy's law. Okay? So disruption, diffusion, and then Darcy flow. Okay, that is what such complex flow dynamics happens in case for coal bed methane flow within the coal seam. Now, how do you calculate GIP? GIP means, what is the full form of GIP? Can someone tell me? What is the full form of GIP? Amal, tell me, what is the full form of GIP? GIIP is what? Anyone? What is gas initially in place? Yes. Thank you, Neeraj. Yeah. Thank you, Krishna. So this is GIIP means gas initially placed. So how would you calculate gas initially in place for coal bed? Okay, you cannot exactly use the same formula for conventional gas. There is slightly a different formula. So the total GIP, yeah, is has two components: GIP free, the amount of gas, which is the free gas which presents in the clit system, and that you can essentially neglect. It's negligible, it's not very high. And then the GIP absorbed, the one that is absorbed in the coal matrix. And the GIP absorbed is calculated using A multiplied by capital H multiplied by rho DAF and multiplied by GCDAF. Okay. So A means the total area, H is the net thickness of the coal seam, so that would give me my gross rock volume, multiplied by rho, that would give me the mass. Okay, that would give me the mass, and then I will calculate that with the gas content that I have calculated, right? Using the Langmuir isotherm that we talked in the last class. Okay, so because we said gas contents formula, gas content unit is gas contents unit is uh, you know meter cube per ton, right? So that means that you have to initially calculate the total mass of the coal and then multiply that with the gas content, and then I will get my gas content for the whole area. Okay. Now that see both of them are expressed in DAF, dry ash free basis. Okay, and this comes, we have talked about what dry ash free, and this comes from the proximate analysis and ultimate analysis of coal. So expect numericals from proximate and ultimate analysis in your exams. Okay, I give you the clue. So you better practice those uh, calculations around proximate and ultimate analysis from Singh's book. Okay, so that is how we will find out the heap of a coal bed. Now, what are the different types of wells which are actually drilled for coal bed methane production? If the permeability is very high, then you generally drill a vertical conventional well, but often you actually frack those wells. Okay, I mean because the permeability is not very high, I mean, compared to conventional gas, you can essentially you have to frack this well. Generally, in coal bed methane projects, there are thousands of wells which are drilled compared to a conventional oil and gas field like 20 or 30 wells. Here, thousands of wells are drilled, and they are generally done in a grid pattern like is shown here. So, what is the grid pattern? Say, for example, I this is my total area which needs to be drilled. I divide the whole area into number of grids of maybe 500 meter by 500 meter or a kilometer by kilometer. So these are 1 kilometer per 1 kilometer grid, and in each grid I drill a well. Okay, so that I can ensure that there are plenty of coal bed methane I can extract. So you can also drill single horizontal well. You can see here this horizontal well's path. This is the vertical part, and then the horizontal part. You can do that, and you can also frac this well in the horizontal part that you can maximize production. You can drill multilateral well. Multilateral means you can see there is one well, one vertical well, and from each one vertical well there are multiple horizontal wells coming out. Now you can also drill multi-seam multilateral wells. As you can see here, there is only one vertical well, and from each vertical well, from every seam, there are four horizontal wells drilled, and from each horizontal well also there are some other shoots coming out from. There is like a large network of wells which is from the same vertical well which is drilled. Okay, not only that, this goes to the next seam as well, and then you again drill more number wells. So it's a fairly complex engineering that you have to do to drill a multilateral multi-seam well. This is very uncommon, of course, but then people have tried it successfully as well. So there is another type of very special well that is drilled for coal bed methane, which we call as the chevron well. And this is the picture of it. This is only done for coal bed methane. So what happens? There is one vertical well, and there are two inclined horizontal wells like this. And then they meet at a single point. Okay. So this particular vertical well is used for dewatering, and these wells are used for gas production. So this is a very special type of well which is actually used for coal bed methane. Okay. So these are some of the coal bed methane wells. As you can see, they are not as complicated as the wells which are drilled for conventional wells. They are fairly simple. They are shallow. Okay, and often they are fracked simply because the permeability is not good enough for to extract hydrocarbon, and often they are fracked. Okay, so that's all I wanted to talk about in case of coal bed methane. If you have any question, you are welcome to ask. Anyone? If not, just I'll just like to highlight one more thing. That is, let me see, where is that? Picture. Just a moment. So if you look here, this is the coal distribution of India, and we talked about this slide before. You know, so currently there is a plan for there is a huge pipeline, gas pipeline, which would actually connect all these coal fields, okay? And that would supply, I think, all the way up to Maharashtra. There is a big pipeline which is being planned by the government of India to actually connect all these coal fields and their coal seam gas production. So that's actually good news. And once this pipeline actually are put into place, what you would observe that there will be some excellent CVM development waiting for near future. So that is one of the areas, coal bed methane, which is quite emerging in case of India, as well as all over the world, because I explained that thing to you about the transition in economy. Okay, so that is something seriously to consider if you want to have a career around oil and gas industry. Of course, coal bed methane is something that is going to stay here for at least next 30, 40 years or 50 years, and is going to flourish a lot. So that is something that you can actually think about seriously of having a career on, because our energy has to go through a transition before we all as human beings start adhering to the renewables. But then of course that has to go through some transition, and these unconventional gases, for example coal bed methane, and you know shale gas is the key. Okay, the other important point here, which I have not emphasized enough, I guess, is the impurities in it's like 95 to 98% CH4. Okay, and the impurities what are present, like sulfur dioxide, nitrogen, carbon dioxide, is absolutely in minimum amount. So the environmental pollution, the environmental footprint that coal bed methane actually leaves is significantly less than any other type of fossil fuels. Okay, it's significantly less. It's pure methane. It actually burns to only carbon dioxide and water. Okay, so and other intoxic uh, elements are really missing. Okay, so that also is a huge um, advantage in using coal bed methane. There are another two aspects that I just want to talk about a little bit. I don't have a slide for that, but that's fine. I'd like to just talk about it. Okay, so you have these very big mines, okay, in eastern India. Say, for example, that is all the way up to from ground. That is all the way up to the coal seam is all the way up to 500 meters, 600 meters. And because we talked about it, the gas content essentially increases a lot with depth. So these coal seams are with extremely high gas content. Okay. So that is good with respect to coal bed methane business, but with respect to coal business, that is absolutely dangerous. Okay, if your coal itself has a lot of methane into it, it becomes very dangerous to mine this coal out. Okay, so the only possibility is first you have to take the methane out. Okay, you have to degasify this seam. Okay, degasify this seam, and then you will be able to mine the coal out. Okay, so there is a two-way opportunity here. One opportunity in terms of you can actually extract the CH4 and use it as a fuel, and the second advantage is while doing that you will degasify the coal seam so that later on you can also mine that coal as well out from it. Okay, so that is one of the important aspects that runs with respect to coal bed methane. Okay, now the difficult part is, of course, one is its environmental footprint, in the sense not itself the gas is clean, but then you have to drill thousands of wells, so you need land actually. So there is an issue around land use and uh, land cover. Okay, land use, land cover. That means you have to actually maybe deforest a lot of area, and also that is one of the challenges. So one of the researches that as subsurface professionals you can do, how to increase the recovery factor of such wells, so that you need to drill less wells and you can get the same amount of production. Okay, so that is one of the issues where you can think of doing research. The other important area is, of course, what we just briefly touched upon, is around its mm, water handling. Okay, what to do with that water handling. That is another important issue which needs to be handled. The final thing that I want to talk on the coal bed methane aspect is the coal seam is thought to be excellent sink for carbon dioxide. A coal seam, excellent sink for CO2. Okay, so that means you can actually sequestrate CO2 into coal bed, and into in neither Fridays or in the Mondays lecture, I will introduce you to carbon capture and storage (CCS). I don't know if you have heard of the name or not, but this is a emerging trend in the industry. Carbon capture and storage. What it means essentially nothing, that if you have, say, for example, a power plant, and that power plant is emitting a lot of carbon dioxide, what do? You trap that carbon dioxide. Okay, to trap that carbon dioxide, convert that carbon dioxide into liquid. Okay, and then you actually pump it back in the reservoir. Okay, in the reservoir which is perhaps depleted. So for example, you have taken out oil and gas from a reservoir, so that means there is low pressure environment within the reservoir because you have taken out the liquid. Okay, so what you can do, you can pump back carbon dioxide into it, and at that pressure temperature the carbon dioxide will not escape from that trap, and you will be essentially emitting the carbon dioxide which would have otherwise been into the atmosphere. Okay, so this is a very interesting technology which is coming up. It has been there for a lot of time. In the UK, in the Netherlands, in the US, people have demonstrated CCS. In Australia, carbon capture and storage, but it has not yet come as a commercial thing. But then once the carbon credit system becomes um, viable in play, okay, you know about carbon credit. What is carbon credit? Can someone tell me? Anyone knows about carbon credit? Who knows about carbon credit? Let's hear it from you. Anyone knows about carbon credit? What does carbon credit mean? Okay, it doesn't seem like you know. So, what carbon credit is essentially that there will be a carbon credit economy. The concept is there, at least people are thinking seriously around it. That if you are an industry and if you are producing carbon dioxide, you cannot recklessly just simply emit it into the atmosphere. Okay. So if you are emitting, say for example, 1 ton of carbon dioxide into the atmosphere, then you have to pay the government this amount of money. As simple as that. Okay, either you choose to pay the government that money, or you have to choose a way by which you can actually will not be able to release carbon dioxide in the atmosphere. So that means there will be a credit system like where you will be responsible for your own carbon dioxide, and you have to all the industries has to find a way to actually put the carbon dioxide back into the ground or in or do recycling. I mean the moral of the story, you cannot emit it in the atmosphere. Okay, so and there will be penalties against if you do. Okay, so then all the companies have to think of a way what to do with that carbon dioxide. Okay, and then this industry, the CCS industry, will emerge. That is what the plan is. The CCS industry will emerge. What it would do, it would essentially buy the carbon dioxide from them. I mean, I mean, it is as if you are giving the carbon dioxide to the CCS company. They will sequester it for you, and then you pay for the carbon dioxide that you have been producing. Okay, so this is what we call carbon credit system, which is going to come maybe in next 10 years, 20 years, who knows? More in the developed countries initially, and then it will percolate through Indian society as well. So that is where the carbon capture and storage is actually getting a lot of focus in the scientific community as well. Okay, so we will talk about carbon capture and storage in detail, but for the time being, remember that coal beds can also be excellent carbon dioxide sinks. That means you can use them as depleted reservoir where you can put the carbon dioxide back into the back into the ground. Okay. So if you have a question, I'll just give you a minute. Otherwise, I'll stop the class here and talk to you again on Monday. Any question? Okay. If not, then I'll stop it here. See you on Monday.